Okay, so now we move on to the granddaddy of all automata, the Turing Machine. So we had diphase and anaphase, and what were they? They were just a finite automata, and the only memory they had available to them was the memory encoded in which state you're in, and nothing else. And we found that diphase and anaphase can only recognize a very restricted class of languages, the set of regular languages. We then talked about context-free languages and the corresponding automata for those. That is going to be a push-down automata. And push-down automatas are a kind of autonoma with memory available in the form of a stack. So it can push things off, it can push things onto the stack, it can pop things off the stack, but can only ever see the top of the stack at any one time. Turing machines are even more flexible. Turing machines intuitively can be thought of as automata together with an infinite tape that stretches infinitely far in both directions, and the Turing machine can whiz up and down the tape, reading and writing to cells as it sees fit. It's much, much more flexible than a tape, and corresponding the class of languages that a Turing machine recognizes is much stronger. So let's just go through all the formal stuff we need first. So formally, what is a Turing machine? Well, what is a deterministic Turing machine? We'll get to non-deterministic Turing machines later. A deterministic Turing machine is a 7-tuple, M, which has got 7 parts, Q, sigma, gamma, delta, Q, naught, B, F. What are all these things? Q is a set of states for the Turing machine. Sigma is the alphabet, that is the set of input symbols. Gamma is the set of tape symbols. Note that sigma, the input symbols, is always a subset of gamma, the tape symbols. So the set of tape symbols is obviously the symbols that are permissible to write to the tape. Q naught is the starting state. B, or sometimes capital lambda, which looks like an A without a bar between, is the blank symbol, and that's a special symbol reserved for telling me that a cell on the tape is blank, as in there's literally no information written there. The blank symbol is a member of the tape symbols, but not a member of the input symbol. So B is an element of gamma, take sigma. Initially, when we have some input to the tape, all other cells of the tape are filled with the blank symbol B, or lambda depending. F is a set of all final states, which is obviously a subset of the set of all states. And delta, which is the transition function. Note this transition function is a partial function, which means it may not be defined for some inputs. Okay, it might be a defective transition function that for some inputs it's just not defined. Okay, so the transition function takes 2 inputs. It takes the current state and it takes the current tape symbol that the tape head is pointing at, and returns 3 things. It returns a new state to go to, it returns a new symbol to write to that cell on the tape, and it returns one of 3 options: left, right, or stay, which tells the tape head to either move to the left, move to the right, or stay where you are. Some authors omit the stay definition. The Turing machine is no more powerful with the stay because you could just have like 2 separate states, one to move left, then one to move right again to sort of emulate the stay command. We include the stay command because it's very convenient to write Turing machines with it. So we represent the Turing machine diagrammatically like we do with most automata. So if I'm in Q1 and I read a 0 on the tape and I transition to Q2 writing a 1 to the tape and I move left, I notate that here. So from Q1, read a 0, write a 1, move the tape head left, and then transition to Q2. Now the language for an automata, well first we find out where to load the input. So initially the tape looks like this. If our input is 101, then we have 101 on the tape. We have blank symbols B literally everywhere else, and we usually assume the tape head is pointing at the leftmost symbol of the input. We could extend that definition and make no assumptions about where it's located, because if it's located somewhere else, we could just like rewind the tape head till we see a blank and then take 1 step to the right. But if the question, we usually assume it's on the left-hand side, but you could generalize that and assume the tape head is anywhere. So what's the language of a Turing machine? The language of a Turing machine is a set of all inputs that halt in an accepting state. First off, what's it mean for a Turing machine to halt? So we talked about how the transition function for a Turing machine is partial. That is, it's not defined for some inputs. So if the Turing machine gets to a state and it attempts to evaluate the transition function and it's undefined, that is, there's no transition to follow, then the Turing machine halts. That is, it stops computation immediately when it attempts to evaluate delta for inputs that are undefined. So if it halts in an accepting state, then whatever the input was on the tape initially, we say that the Turing machine accepts that. So the Turing machine, the language of the Turing machine is a set of all inputs that halt in an accepting state. Okay, cool. We can sort of formally write that out here, where delta star is sort of like an informal notation from Q naught. If I read W, the Turing machine will halt in a final state. And we also consider, so that's one thing to consider about a Turing machine, is the language it accepts. The other thing we consider about a Turing machine is we can think of a Turing machine like a computer program. And computer programs read in input and spit back output. So we can also consider what the Turing machine actually does to what's on the tape. So if some Turing machine M, given X on the tape, halts with Y on the tape afterwards, we say M of X equals Y. So we can treat M like a function in Python, right? Like a computer program. Sometimes M might get stuck in an infinite loop, just like if you write a computer program that sometimes gets trapped in an infinite loop. And we denote this, if M gets trapped in an infinite loop when X was on the tape to begin with, we say M of X equals turnstile, which is a little upside down T. A total Turing machine is a Turing machine that halts given any input, so it never gets trapped in a loop. And a partial Turing machine is a Turing machine that for some inputs can get trapped in infinite loops. Okay, and so that's all the definitions you need for a Turing machine. The next video is going to go through examples of Turing machines, how to evaluate their behavior, etc., etc. And I'm basing the majority of this content on this textbook here. Introduction to Automata Theory, Languages and Computations by Hopcroft, Motwani, and Ullman. It's a really good book. It, in some cases, goes a little bit beyond the scope of this course, but Chapter 8 covers everything you need to know about Turing machines. I'd really recommend getting a copy of this book. It's really good, and it certainly explains both Turing machines and autonoma, and basically everything from like week 7 onwards in this course, this book covers on a very high level. So I would recommend getting a copy of this book. It's good study for the exam. There's the title again.